So, what if I told you that one of the most devastating hacks in history, a trick that's been bringing down systems for decades, all starts with a super common coding mistake? Yeah, one that's surprisingly easy for anyone to make. This is the buffer overflow, and today we're going to tear it down and see exactly how it works. It sounds totally nuts, right? I mean, how can a program just asking for your name be so fragile that typing a few too many letters could not only crash it, but literally hand over the keys to the kingdom to an attacker? That's the mystery we're unpacking today. All right, so to really get how this works, we need to look at the flaw itself. And listen, this isn't some crazy, complex, cryptographic failure. Nope. It's a really basic mistake in how a program handles the information you feed it. Okay, think of it like this. In programming, a buffer is just a temporary storage space. Basically, it's a mailbox. And this mailbox is built to hold a specific amount of data, say, a small letter. A buffer overflow is what happens when a program tries to shove a giant package into that tiny mailbox without even checking if it fits first. The package busts the mailbox open, and all the contents just spill out everywhere. Now, a simple spill might not seem like a big deal, but in the digital world, that spillage is exactly where the danger is. So let's get into how attackers can weaponize this one simple mistake and turn that tiny crack into a wide open door. So here's the crucial part. When the program writes way more data than the buffer can actually handle, that extra data doesn't just, vanish. It gets written right on top of whatever happens to be next to it in the computer's memory. And what's next to it can be really, really important stuff. Let's just walk through the steps. It's pretty simple. First, the code creates our mailbox, a buffer built for just 10 characters. But then, in step 2, it uses this notoriously unsafe function that never bothers to ask, hey, how big is this package? So when an attacker in step 3 types in a 30-character name, well, those extra 20 characters spill out and start overwriting other critical parts of the program's memory, like the actual instructions telling the program what to do next. Now, there are a few ways attackers pull this off. The most classic method is the stack-based overflow. You can think of the stack as the program's short-term memory and its to-do list. It keeps track of what it's supposed to do after it finishes a task. So by overflowing a buffer on the stack, an attacker can just scribble over that return address and trick the program into running their malicious code instead of its own. It's a brilliant, devious little trick. So, why go through all this trouble? What's the end game here? Well, it's definitely not just about crashing a program. It's about what you can do once you take control of its execution. The simplest goal, is just to crash the program. That causes what's called a denial of service. But the real prize, that's code execution. If an attacker can overwrite the program's instructions with their own, they can do anything the program could do. And if that program happens to be running with high-level permissions, the attacker can achieve privilege escalation, getting root access, which is basically total, complete control of the entire system. Game over. And, this isn't just some theoretical thing we talk about. Buffer overflows have been at the very heart of some of the most infamous cyber attacks in history, and they've literally shaped how we approach security today. I mean, think about it. All the way back in 1988, the Morris worm used a buffer overflow to crawl across the early internet. Then in 2001, the Code Red worm did the same thing to Microsoft web servers, but on a massive scale. And more recently, in 2014, the Heartbleed bug, which was technically a buffer overread, but it's the same idea, used this flawed memory handling to leak secrets from a huge chunk of the internet. It's the same fundamental flaw, just popping up again and again, year after year. The good news is, we've learned a lot from all these attacks. So how do we actually defend against such a basic flaw, How do we build better digital mailboxes? Well, the most direct defense is just writing smarter code from the start. The program you see on the left blindly accepts any size package, but the one on the right is way safer. It measures the package first. In programming, this just means using functions that actually check the length of the data before writing it to memory. It's as simple as measuring the box before you try to stuff it in the mailbox. But secure code is just one layer. Modern systems use a whole bunch of defenses. For instance, compilers can add something called stat canaries. Think of them like those digital die packs in a bag of money. They're placed right next to important data. If an overflow happens and that canary gets disturbed, the program just shuts down immediately. Another great technique is ASLR, which constantly shuffles the program's memory layout around. This means even if an attacker breaks in, they can't find anything because all the addresses have changed.
All of these layers, plus regular software updates, create a much, much stronger fortress.
But in the end, it all comes down to this. While all those patches and modern defenses are absolutely crucial, the best protection, by far, is to prevent the vulnerability from ever existing in the first place. It's all about building a solid foundation instead of constantly trying to fix cracks. And that leaves us with a final, kind of sobering thought. We have built our entire modern world on top of decades and decades of code. And a lot of it was written long before these defenses were even a thing. So while we know how to prevent buffer overflows today, there are countless old vulnerabilities probably still lurking out there, just waiting for the right person to find them. The question isn't if we'll find another major flaw, but when and what's it going to be?